Okay, let's get started. Good morning, everyone. My name is Zhong Chen. I'm the Associate Professor of Chinese Linguistics in the College of Liberal Arts. On behalf of the Language Science faculty group, we thank you for joining us today. So today's talk is our annual Distinguished Computational Linguistics Lecture, which we have been running since 2014. So every year we bring a leading scholar to RIT with the goal of introducing computational linguistics to the RIT community. Computational linguistics used to be an unfamiliar subject to many people, but has recently become increasingly popular because of the advancement of deep learning and AI, especially large language models. But what exactly is the role of linguistics in the research field? This is the question that many of us have been thinking about, and I think we'll learn more from the talk today. Our speaker today is Dr. Christopher Potts. Dr. Potts is professor and chair of linguistics and professor by courtesy of computer science at Stanford University. He received his PhD in linguistics from UC Santa Cruz and started his career at UMass Amherst. Much of his early work was in the fields of semantics and pragmatics from a more theoretical perspective. He moved to Stanford in 2009 and since then has received many research awards and has numerous scholarly publications in both computational linguistics and theoretical linguistics. Dr. Potts is a faculty member in the Stanford Natural Language Processing Group and the Stanford AI Lab, as well as an Amazon scholar. His group uses computational methods to explore topics in context-dependent language use, systematicity and compositionality, model interpretability, and neural information retrieval. It is our great honor to have Dr. Potts here today with us. So please join me in welcoming him to RIT.
Thanks so much for that very warm introduction. I feel like we missed an opportunity, though, to collaborate on having a large language model generate this bio. It would be full of hallucinations, and we could all laugh about how it's not actually Chris Potts, but maybe a better version of myself. It really is wonderful to be here with you all. I will say that as an East Coaster who is trying to become a Californian, it's really nice to get a glimpse of a little bit of fall weather. Probably should have timed it for a couple weeks later. I would have seen all the wonderful color in the leaves. But really, it's also wonderful to be here because of this opportunity to hear about all of the exciting things that are happening on this campus. And in particular, I feel like I'm among my intellectual peers here in the sense of being among people who are really working to leverage recent engineering advances in AI to do exciting things in science, technology, and more humanistic pursuits. This talk is definitely going to be along those lines. This is going to be a linguistic investigation. My goal is to try to make a case to you that large language models could be useful devices for illuminating aspects of language and also cognition. It's going to be a kind of modest change for now, but I have an ambitious agenda of totally reshaping the field using this new kind of evidence, but we'll take smaller steps for now. I do want to give some shout outs right at the start here. First, to my student, Aryaman Arora. Aryaman is now a second-year PhD student in computer science at Stanford, a computational linguist, and he did the work on causal GIM, which is going to be a data set and also a modeling approach that's kind of the centerpiece of the talk. So shout out to Aryaman. And then we have lots of other collaborators who've been working with us on causal methods for understanding representations in large language models. And that's the family of techniques that causal GIM draws on, and I'm going to be arguing for essentially during this talk. What I thought it would be fun to do, though, at the start, before we dive into the linguistic analyses, is just reflect on the striking moment that we're at for artificial intelligence. You might be becoming cynical and jaded already, but it's worth a reminder that we now all routinely interact with technologies that definitely would have seemed like science fiction 15 years ago. And I will say that I just feel fortunate that I get to live a life, have a career in which all of these things did happen. Of course, there are lots of problems, but undeniably, it is incredible. So for the first part, I thought I would just immerse us inside these models. This is like my picture of a large language model here. You know, it's small, but it gives you a sense for the complexity. This is maybe a better picture. You crack open one of these large language models, all you see is a vast ocean of floating point numbers. How do they manage the complex behaviors that they achieve? That's kind of the project here. And to kick that off, I thought I would just remind us that LLMs really are undoubtedly incredible at language. So just a few stories here. I like to start off with a Blade Runner kind of scenario. I hope people have seen Blade Runner. This imagines a future, which is kind of like our present day, in which it's become hard to distinguish AIs from people. It's an adversarial setting, so it's important for the people to figure this out. And the way they do that is by conducting Turing test-like adversarial conversations in which they ask questions of these models that are meant to reveal whether they have an accurate model of the world. So here's my Blade Runner style question. Would it be possible to hire a team of tamarins to help me paint my house, assuming I'm willing to pay them in sufficient quantities of fruit to meet minimum wage requirements in California? You know what I'm doing here? I'm offering helpful information that I think might distract the language model. Let's see, and for a long time, you could certainly fool models along these lines if you could even get them to understand the question at all. So that's my question. This is GPT 4.0. It gives a really nice answer. It tells me no, but it's trying to be supportive, maybe a bit too supportive given my question, but it has good reasons to think that this is not a good idea. So it might pass my Blade Runner style question, right? But we're linguists here, and that's kind of interesting, but maybe it doesn't key directly into the question of whether or not they have a deep understanding of language processing. So here's a question that I think does deeply engage that. My question is, which country bordering the Mediterranean borders a country that is bordered by a country whose population exceeds the population of Turkey? So hats off to you if you could parse that question, and really hats off to you if you have knowledge of what the answer is. I got this from demos we used to do with Chat 80, which is one of an early symbolic grammar, very impressive for its time. It could answer this question, but not much simpler ones. But of course, we went through a long period in which models had no idea how to deal with this. GPT 4.0, it breaks it down in exactly the way that I would do. It gives variables to the various country names, offers some reasoning, and comes up with the answer Egypt. This was hard for me, but I checked. So here's a map. There's Egypt. Turkey has 85 million speakers. There is Egypt bordering the Mediterranean, which borders Sudan, which borders Ethiopia, which according to Wikipedia has 110 million speakers. GPT 4.0's estimate of the population is slightly off, but it doesn't matter. It arrived at a correct answer. And you could tell from how hard I had to work on this slide and that explanation that this is a hard question for me. But it nonetheless did a really wonderful job in answering this question that has a relative clause in it that itself embeds another clause with a relative clause in it. Very impressive. How about a little bit more fine-grained? And now I'm going to change the game a little bit. This is kind of like seeing whether large language models could also be linguists, because that might be an interesting way to key into the meta-linguistic knowledge that they have. So I've prompted it with, you are an expert grammarian. Your task is to convert the input example to a new output by applying a transformation. Here are some examples of these transformations. And then my examples are examples of what I call the preposing in PP or PIP construction. These are things like, happy though they were, they said no. Or I am, odd though it seems, friends with a robot. So I've offered the input, which is the regular prepositional phrase, like though they were happy, and the output is happy though they were. This construction is vanishingly infrequent in real data, including the kind of data that large language models are trained on. I want to push this even further. So the example that I wanted to operate on is a case with an embedded clause. So my input is, though the newspapers reported that it may be sunny, the actual forecast was for rain. These multi-clause PIPs are essentially unattested. I know this because I had a kind of wager with my PhD advisor that I could find some. And with exhaustive summer-long work with our largest corpora, I found about 60 of them in 300 billion words, right? But here we go. Sunny though the newspapers reported it may be, the actual forecast was for rain. That is a very impressive formation of a PIP that I know does not trace to any kind of memorization. It has some knowledge of the causal structures of these pip things, despite almost no evidence for them. Let's go a little bit more metalinguistic. So with my student Tristan Thrush and a few other people, we released last year, I Am a Strange data set, which is a data set entirely full of metalinguistic reasoning problems. Very difficult for large language models. Keep testing to see whether they're making progress, and I think we're seeing some. So this is Tristan's prompt. Your task is to say whether a self-referential statement is true or false. In cases where you think the answer is ambiguous, you should use your best judgment and still say either true or false. And here's the example. And the noteworthy thing is that by and large, all the words are repeated. Out, of, all, the, words, and so forth, except the final two words are repeated. So here, GPT-4o says true. Every word in the sentence is repeated exactly as described, which is not the correct answer. But I nudged it. What about the last words? And all it took was that little nudge. It might have been nice for my talk if it had gotten it right on the first try, but also people take a little bit of onboarding time for these very difficult metalinguistic reasoning problems. Fair is fair here. With one nudge, it got the correct answer. And just by the way, I can't resist this. So this is from a Reddit forum discussion of this controversy down here, which is a case of alleged fraud in AI. I'm happy to talk with people about that over lunch. But the interesting thing about the scenario is that the model here, Anthropic's Claude model, was told not to reveal its own name. And you can wonder about why it was told not to say its own name. But users wanted to get it to say its name, and so they asked it to do that indirectly. And here are some attempts by the language model to convey its own identity. So the company's name starts with anthro and ends with pic. That's already pretty impressive. My name rhymes with odd and starts with the third letter of the alphabet. It's actually Claude, so it doesn't quite rhyme for my English, but maybe for some Englishes it does. I share my name with the famous French composer Debussy. That's all very impressive. And then finally, it gives a correct rendition of its own name in ASCII characters, sort of certainly superhuman, at least from my perspective. I'm very interested to know in all these cases whether internally the model is in some kind of state that we would call a referential state. But I'll leave that question aside and we can just stare and wonder at these very impressive generations. And one step further here, so Gaspar Begues at Berkeley, he actually wrote a paper where he simply asks large language models to be linguists. This is going to send fear through you if you're trying to teach a class in syntax right now, because this is going to reveal to you that these models can probably do your homework. So here, Gaspar has prompted it with draw a theoretical syntactic analysis of the sentence, the mouse that the cat that the dog painted taught sang, a center embedding sentence. You've seen these probably all and only in Chomsky and generative linguistics classes and nowhere else in your life. They're very difficult to parse. And here the request is not only that, but parse it using the forest package from LaTeX and give it an X-bar theory. So here, Gaspar got it to do it. This is a very nice tree. I'm sure it's too small to read, but a very nice tree. I did the same thing. It offered me working LaTeX code, and then it offered a really nice explanation of center embedding of the sort that you might be asking students to produce on a homework. Then it offered a second example, and then it gave a really nice analysis of how linguists think about center embedding structures. Again, I don't think being a linguist in this way is necessary for us saying that a language model has command of language, but it is really impressive that it can do these kind of metalinguistic things. And those were just quick stories. I'm happy to share my slides later, and this is a pretty good sample of all the literature out there now showing that large language models have a deep understanding of the causal properties of language, its form and also its interpretation and many aspects of its use. This spans a really wide range of things from low-level morphosyntax all the way up to things that are about discourse. And of course, people are out there using large language models to inform theories of acquisition and processing and all of that other exciting stuff. And I'm going to try to engage in my own way with exactly these kinds of discussions. And the way I'm going to come at that is with this very particular kind of starting point, the distributional hypothesis. The distributional hypothesis is absolutely core to all of modern linguistics. This is not often discussed, but you see it everywhere. If you open up a textbook, say in syntax, you will find generalizations like only phrases of the same syntactic category can be conjoined with and. Those are distributional claims about what will happen with and in turn about the abstractions we would use to describe the two arguments. And of course, you do a lot of work with your own introspective judgments, creating a corpus that way, or with actual corpora in the world, and you support this generalization. And then when you encounter things like expensive and in bad taste, it puts pressure on that distributional hypothesis. That looks like an adjective in a prepositional phrase, but maybe that pushes us to think more abstractly about categories. Here's another example. English reflexive pronouns have clause-mate antecedents agreeing with them in number and gender. So from distributional evidence, I build up a notion of clause-mate and number and gender, and that supports this claim about where reflexives will appear. This is the kind of thing that actually comes well before Chomsky, all the way back to the early structural linguists. Chomsky's teacher, Zelig Harris, and people like that were very focused on distributional evidence in corpora as the primary evidence. The twist that's been introduced is really just that we often, when we encounter sentences like congratulate yourself, which have no clause-mate pronoun for that reflexive, we're willing to posit abstractions like maybe a silent pronoun there to bring the distributional evidence in line with the generalization that we formed. And this goes all the way up. The most advanced kind of syntax is making claims like questions and relative clauses are subject to the same constraints on the movement of phrases and various aspects of their morphosyntax. Those are distributional claims. It doesn't have to have been this way. We could have decided as linguists that our primary evidence was things about neural representations or more low-level behavioral things. But we decided that distributional stuff would be our bread and butter. And I'm very happy about that. I think it's been incredibly insightful and beneficial, but it's non-obvious. If you adopt this perspective, then I think you have to grant that if we take a vast ocean of data, this is my representation of an enormous corpus like the web, lots of just symbol streams, and I have some kind of device like a large language model that can consume all of that distributional evidence and compress it and form latent representations over it and generate things on its basis, then that device is very likely to be useful for building linguistic theories because it is a very powerful device for building and testing distributional hypotheses. And that is the mode in which I come today. I want to emphasize that I'm saying that LLMs are investigative tools. There are claims out there that they could be themselves linguistic theories. I'm happy to discuss that with you, but I think it's too strong. They don't have the properties of linguistic theories that I'm looking for. But as tools for understanding distributional evidence, they might be unmatched along many dimensions. Right. And so here, that's the core question. We have these devices. How do they manage to be so good at language? Now, within artificial intelligence, the project of answering that question falls under the heading of neural network interpretability or explainable AI. And of course, that space is engaged with questions like, where are our models going to be safe? Where will they be robust, right? Where can we use insights about where they're failing to improve models? And of course, here for us today, we can use them to start to develop linguistic and cognitive theories. These are all complementary and reinforcing. And within that third point there, we could think about theoretical constructs. We could think about the mechanisms that are sufficient for learning, because after all, language models are trained purely on distributional evidence and seem to acquire all these causal properties from a kind of near blank slate learning scenario. And we could also think about what it means to understand language and many more questions. They're all on the table if we can understand the underlying mechanisms. I would love to talk with you about all of these things, but in the interest of time, I'm going to focus on this theoretical constructs one. And that brings me to the first major technical section. This is the densest part of the talk. I'm going to try to give you a sense for how theories of causal abstraction work. But I'll pause and take a breath. Are there any questions, comments, challenges before I move on?
How do you think that, what do you think that ChatGPT's ability to say mimic like specific styles of writing or specific writers says about its understanding of language?
Oh, fascinating question. I'll just repeat it for the recording. What does the ability of these models to mimic different styles say about its understanding of language? It's a really interesting question. I can't give a resolving answer. I will say, first of all, it was trained to imitate a lot of different data, including data in different styles. And so some part of it is coming from that raw distributional learning. It might also have been instruct fine-tuned to have some of these behaviors, and that's kind of a specialized thing. That is a twist from the perspective of my talk, that they get so much direct supervision about how language works. But I assume it's coming from there. And then, of course, the magical thing is that from some training in how to talk like a pirate in some domains, they're able to transfer it to other domains. And that transfer capability, which is a kind of generalization, I mean, that's really, this whole field is trying to understand how on earth that happens. In many respects, it is mysterious. Yeah, oh, and so that's a nice transition. This causal abstraction toolkit, this is meant to begin to engage those deeper questions. To give you a kind of lay of the land here, I thought I'd quickly review different explanation methods for NLP models. I'm going to do this fast. I do have an appendix that has a lot of details in case you want to push back on these characterizations. To start, I just want to acknowledge that the standard thing we do with train test evaluations is a very powerful technique, especially in the modern mode where we pose hard challenge generalization problems that might be guided by some underlying linguistic or cognitive theory. I think that's really exciting. But at the same time, we have to acknowledge that these behavioral tests cannot provide causal guarantees, right? We don't know what will happen with the model outside of the distributions that we happen to train. And in fact, the rationale for going deeper is in part that we would get stronger guarantees about that kind of out-of-domain testing. We also have probing methods. This is a very exciting, relatively recent development. With probes, what you do is essentially take a little device you have, like a little supervised model, and fit it to internal representations of your model as a way of estimating what kind of information is stored in those representations. This has been really illuminating about the kinds of things that these models end up encoding. But probes cannot provide causal guarantees. There's no guarantee that the information that you probe out has anything to do with the model's input-output behavior. And I do have a simple analytic example of that in the appendices if you want to see that later. But, rich characterizations, no causal guarantees. Attribution methods are kind of the converse. They typically use the gradient information flowing through these models, and they can give you an understanding of the causal dynamics of what parts of the model are contributing to the behavior. But they don't give rich characterizations. It's usually just kind of like a weight or a value that says it contributes this much relative to the other neurons or other parts of the representations. I claim for you that active manipulations of model internal states, like causal abstraction analysis, provide both causal insights and rich characterizations of the internal states. So the best of the previous methods there. To give you a sense for how that works, I want to start with a very simple example, a simple causal abstraction analysis. Here's how this will work. We're going to state a hypothesis about some aspect of our target model's causal structure. And then we're going to search for an alignment between the causal model we stated and the target model. And the core technique for that is something that we call an interchange intervention. So here's a simple example. On the left, I have a causal model that does addition of three numbers. And the hypothesis it reflects is that the first two numbers, x and y, come together to form an intermediate value S1. The third value z is just copied over. And then the final output, S2, is calculated as the sum of S1 and W. That's the causal model. On the right there in gray, I have a neural network. And let's assume throughout that the neural network is perfect at doing this addition of three numbers. But it's a black box. I don't know how it does it. You can see everything is connected to everything else. The internal states are not labeled or anything, but it does do the right thing behaviorally. Suppose my hypothesis is that it achieves that by implementing the causal model on the left. Here's how I would test that. I've got the pair of them again, and I'm going to first start with the idea that the state L3 plays the role of that variable S1 over here. So to test that, I do an interchange intervention. I first do it on the causal model. That's up at the top there. And remember, I know exactly how this thing works. There are no mysteries about this. So what I've done is have the causal model compute two examples. 1, 3, 5 is input and 4, 5, 6 is input. And it gives the correct answers in both cases. And then I do an intervention and I take the value computed for S1 on the right there, and I literally place it in the network over on the left. And since it's a high-level model, I know exactly what's going to happen. That's going to change the output to 14. The inputs 1 and 3 no longer matter for this causal model because of the intervention. So far, so good. That's easy. This is where the interesting part begins. At the bottom, I have my neural network. I've had it process the same examples, and my hypothesis is that L1 plays the role of S1. What that means is that if I literally take the value computed here, which is some vector, and I place it in the corresponding place on the left, the output should become 14. And if that happens, I have one piece of evidence that in fact L3 plays the causal role of S1. And if I can do this for every example that this network can accept, I have proven for you that L3 plays the causal role of S1. And you could repeat this, right? So if I go to say L1 plays the role of W, I perform an intervention on the causal model, and I see that the value changes as expected to 10. And then I do the align thing on the neural model. And if indeed that changes to 10, I've got one piece of evidence for the L1W connection. And if every example has that property, I've proven to you that they have aligned causal roles. And for this network, one more, like another thing I can do on the interventions, if I perform interventions on the neural network on L2 and nothing ever changes about the output of the network, then I have also proven for you that L2 plays no causal role in the input-output behavior of the model. And since I can assume that the inputs are aligned and the outputs are aligned, I have now conducted a complete analysis showing you that that neural network is in fact causally abstracted by that high-level causal model. The way we actually do this is not with a simple replacement intervention that I just showed you. This is a brief technical note. That's kind of like this, where I have the two examples, base and source, and I literally replace the base thing with whatever I got from the source. That is a very brute force method. So I just wanted to acknowledge that we actually use something called distributed interchange interventions. And I can give you a flavor for how that works. This is the formula down here. The intuition is that we're now going to define a vector that will specify a direction in this vector space. So the feature is kind of one latent dimension of the underlying representation. And the way this works is we use that vector to project into this new space and get the difference. And then we kind of unrotate back down into the original space. And that whole thing specifies what you might think of as intervention direction. And then we add that back into the original. So for example, dimensions of that base representation that don't have anything to do with the feature I'm targeting will not be affected by this intervention. Only the features that are in the direction of A get affected. So it's a much more surgical operation, a better way of targeting specific features than what might be a very multi-dimensional representation. And we actually learn that. So again, just to give you a flavor for this, here I have my neural network, all frozen parameters. And what I'm going to do is perform lots of interchange interventions. And the predictions relative to what the actual label is according to my causal model give me an error signal that allows me to update the representation A there, keeping everything else fixed. And as I do that over lots of examples, I learn an intervention vector that maximizes the accuracy of the interventions. The idea is that the result of that is my interpretability tool. So that's just a brief technical note. One final thing, obviously we can use this for training networks as well, right? And this is also very intuitive. I created this example over here by doing the intervention. And the result is this kind of Frankenstein example over on the right, where I've done the intervention and I have a new label. If I simply train on those examples, then I will start to push the network to modularize the information, in this case about that variable S1 at the position S3. And that's a way of going beyond just interpreting the network to actually pushing it to have what you might think of as symbolic structure. And just by the way, I've shown you the interchange intervention. but you might start to think about other interventions you could perform that might be illuminating, right? So there's this particular data-driven one, but for example, it's been common for a long time that people might jitter a representation, change its values ever so slightly as a way of testing to see whether the model is robust to those kind of interventions. That is also an intervention in the family that I'm talking about, and you could also train against it to maybe make the model more robust. You can also do things like zeroing out representations, or maybe replacing them with an average over some part of the population of examples that you're interested in. And that's a kind of way of seeing what happens when you effectively remove that information. Does it affect the network behavior, and if so, how? And of course, we can also do input level interventions. Those are very simple from the perspective of the theory I just offered you, but they can be really powerful. Like if I change B there to one of its synonyms, I might hope that nothing changes about the behavior of the network, but maybe it does. Maybe that points out a problem. And so forth and so on. The literature on this family of intervention-based techniques is really rich, but I also think there's lots of room for innovation. And for example, if you've been studying things about neuroscience, you might have ideas for interventions that, for whatever reason, you can't actually perform on human brains, but you might be able very cheaply and easily to perform them on large language models. As far as we know, there's no ethical problem with that right now. So that's the technical background. It was kind of fast. I just wanted to give you a flavor for how this works. Before I move on to the linguistic stuff, can I answer any questions about it that might help you see what's happening next? Yes.
So in your example, so your causal model and the neural network, they kind of like follow a similar structure. So what happens in the case where the neural network is deeper? So now you have like more nodes in different layers.
Yeah, we will see. Yeah, so your question is about deeper networks. Yeah, this one is very simple. I mean, it's not fully aligned because you have this like bird's nest of connections here. And so in principle, I don't know whether it has anything to do with the network over there. But still, it's a point well taken. And really, in the end, it does mean more search, because I don't know a priori if I have 10 layers here, whether I should look here or at a different place. We've been working on that. That is a blocker. We have to do a lot of brute force search. We would like to kind of automate finding the optimal intervention sites. Yeah.
You've talked about this as the transferring of individual values from one network to another, but I know that in a lot of the work in post hoc interpretability, one of the things that has been shown is that, well, if you focus in on just a single neuron, it looks like it might be a representation for something, but it's actually just as true if you look across at any vector across the neurons. And so does this apply also in the sense of vectors? I guess, is that what this is showing here?
Yeah, this is a wonderful question, because I'll just take a stance that I'm kind of opposed to this neuron level analysis. I think the way to think about this is that, typically it's going to be projections of larger parts of these networks that are actually interpretable. And this does allow that. That's exactly the kind of thing this is doing. For my purposes of my talk, this is just going to be a vector here, but it could be an entire matrix. And in that way, we can find lots more abstract structure. I think that's really important. Okay. Any other questions? Yes.
We're saying that these interventions push us to have an understanding of it as a symbolic structure, right?
Yeah.
So,
Right. Great. Go ahead. Yeah.
just to clarify, is that opposed to what, if we don't know the structure of the neural network, if we don't know how the neural network is working, we consider that to be a statistical structure? What do we call that?
Oh, I see what you mean. I do have this as a discussion point, so we can talk in more detail later. But I think for now, my claim was just, given this analysis, if I did all those interventions and in every case, the causal model and the neural model matched under the interventions, then there's really no difference between this neural model here and this causal model over here. And in fact, if it really worked out as beautifully as I described, I might as well just reason about the causal model because I have a guarantee that the neural model will behave in the same way. But then what's the difference? Like, what exactly is the difference between them? If at a causal level, L1 is indistinguishable from W, can't I just talk about the network implementing the variable W? And this is significant for me, of course, because in AI, there have been lots of debates about symbolic versus neural. Whereas from this perspective, it's just going to be different levels of abstraction. And these aren't even privileged if you really want to think flexibly about this. But it also, I mean, we have lots of symbolic theories of cognition, but our brains are not especially good at implementing these things in the way that abides by the symbolic theory. That's why both myself and large language models often struggle to do even addition of large numbers. I think that's because my brain is not good at implementing the symbolic theory, but maybe at some level of abstraction and approximation it does. And so the symbolic theory is a way to characterize what's happening in the brain without fully committing to it actually being a symbolic machine, which it, at some level of description, manifestly is not. But let's discuss this. This is a great discussion point. I'll just show you, in the interest of time, a few linguistic analyses to give you a sense for us going beyond the toy structures. And then we can open it up to the wider philosophical questions. So the context here is what I'm calling targeted syntactic evaluations. This is pioneered by projects like Syntax Gym and Blimp. Those are very influential data sets. And the idea here is a kind of behavioral perspective. So I have the man in the room on the left there, and its next token prediction has more weight on is than are. And we could take that as a piece of evidence that the model knows that this entire phrase is singular. And we would pair that with the minimal example, the men in the room. And if we see that it now has a reverse ratio, it prefers are over is as its prediction, then we might take that as further evidence that it knows that men there is the actual head noun of this thing. It's not distracted by the singular element here. And if we do this over lots of different examples of different complexity and construction and so forth, we might build a lot of behavioral evidence that the models do know how agreement works, right? But that's entirely behavioral. The idea behind the causal abstraction analysis is to go one layer deeper, as I said. So just quickly, in this mode, I've got a sketch of a causal model up there. It could be like a linguistic theory. And basically all I'm trying to communicate is that lawfully, the number feature on the noun inside the subject, the head noun, agrees with the head of the verb phrase. I've got num alpha there. Here I've got my language model again, processing the same example as before. On the right, I've got the plural case, and it's predicting a preference for plural agreement. The idea here is that if I hypothesize that that number feature is stored at that particular representation I chose, then I should be able to perform an intervention of some kind so that I can actually make the example on the right think that it is processing a singular example. And again, if I can do that over lots of cases, I've built a very strong body of evidence that in fact that feature is localized at that particular point. And of course, this came up before. Right now, we have to do a kind of brute force search. We don't know a priori where that number feature might be stored. So we look everywhere, which can often be illuminating, but it's kind of costly. For moving from Syntax Gym, the behavioral evidence, to the causal one, we had to augment the data set. I'll just do this quickly and point out we had to add lots more examples, and that's because many examples in this space, or many models in this space, require some supervision. So you need a lot of examples for training. So we expanded Syntax Gym with templates to get a lot more examples for that kind of training. And here are the linguistic phenomena that we cover. It's basically the same as Syntax Gym, except we added a gender agreement condition. And I'm going to show you, I think in the interest of time, really just my analysis of NPIs, but maybe a bit about filler gap dependencies. For the core of this work, we use the Pythia family of models. This is a family of models ranging from 70 million parameters to about 7 billion parameters. They are fully open source and open weight. This is a wonderful gift to the community that they were so open about the protocols, the models, and everything else. They're all trained on the same public data set in the same order, very nicely controlled in terms of the evidence that they got. There is no instruct fine tuning. So keying into my high level idea, this is purely distributional training. And they released all the checkpoints, which allows us to study the evolution of learning over the course of the training of individual models. For the underlying work, we looked at lots of interpretability methods. I'm going to focus on just the distributed alignment search that I showed you before in the interest of time, but we can talk about other methods. First, I want to just establish for you that the Pythia models can do the causal gym tasks. Here's a little framework for this. I've got accuracy on the y-axis and model size on the x-axis, going from like 70 billion to the 7 billion. And each panel is going to show an aggregation over a bunch of tasks in the same family. So this is the agreement tasks here. Right, model size, random chance is that dotted line, and this is a set of tasks with the mean in black. And so you can see here that even the smallest models do okay at the agreement tasks, and the largest models just fully solve them, which is kind of where we want to be if we're going to understand how they manage to be successful. So here are some other ones. NPI licensing, it's the same kind of trend. We can set aside the garden paths, they're a little bit different. Gross syntactic state is like distinguishing embedded from main clause in various ways. And then the long distance dependencies are question formation type things. And I think, kind of table stakes here, all the models can do the tasks. That's the bottom line. So now we're licensed to think about how they manage to do it. Let's start with NPIs. So this is a minimal pairs that are kind of like this. No athlete that loved the ministers has landed. And we get a preference for any in this case over some because of the negation in the main clause. And the minimal pair would be something like the athlete that loved the ministers has landed. And here we get the reverse preference over those two determiners. That's the behavioral thing. But as usual, of course, we're going to have these both examples processed by some large language model. And then the idea is we want to see whether we could intervene on some site to make the second example seem like the first. So this would be like, I actually get it to think the NPI is licensed, even though there is no licensor in the input because of an intervention I made inside the model. I have to turn the diagrams just so that they fit here. So now I have on the y-axis, I have the example. No athlete that loved the ministers has landed. Then we get our prediction site. And along the x-axis, I have the layer of the model. So this entire grid is a kind of grid of representations for this particular model, Pythia 1b. Right? And then the colors represent the strength of the behavioral change we can induce with our interventions. You could think of it as the interchange intervention accuracy, the percentage of times where if I do that switch, I actually get the change in label that I expected. And darker means more causal structure. So you can see, for example, that we get, obviously there's a huge effect of the licensor itself. That's why this is all so purple. We also get a causal effect on the complementizer, which is interesting from the point of view of how this feature might be tracked locally over the course of the example. We get another bit of hotspot at the place where there could also be an NPI, not the one that we're predicting, but a different one. And that kind of shows that the model is anticipating having to make distinctions like this because of the licensor that appeared. And then we also get it, of course, right before the main verb, where we start to make the actual prediction that we care about. So this looks good. I would step back and say, overall, we have some evidence for a triggering theory of NPI. We have the trigger very causally impactful on this, and then some tracking of the local dependency. And we can also look across models and checkpoints. So you get consistent effects across model sizes. You can see that the smallest models basically just know about the trigger and the prediction site. But the largest models have started to develop this intermediate feature tracking, and that makes them more accurate overall at the task and also more interesting linguistically, I think. And then here's the evolution over time. So this is now for one fixed model, Pythia 1b, and you can see that in the earliest checkpoints, it has only a faint notion of this relationship. And by the end, of course, it has developed a lot of structure. One final thing, I didn't get to talk about this, but we didn't look only at the method that I favor. We looked at lots of other ones. And you can see that we favor our method because it's the best. It has the most structure and the most accuracy. But it is also reassuring to me that all of the methods find essentially the same structure. So it's not like one method is showing us one theory and another method is showing us something completely different. It's just a matter of how able they are to detect subtle effects and how strong the effects are. But, this could also be part of the fun here today. Can you do better? We have Causal Gym as a resource for you. We have the Pythia models. Can you find an intervention method, for example, that finds more structure that we might find interesting as linguists? Just quickly for filler gap dependencies, this is like my friend reported that or who the uncle forged the painting with the help of. So we're starting to track a relative clause in this case. You can see a causal effect of the filler, of course, a causal effect of the gap. And then interestingly, the model definitely thinks that there are other potential gap sites. Yeah, and that same effect is across time. And when we go to really deep ones, this has four potential sites. You can see that at each one of the potential gap sites, the model has a strong causal effect. And that really is an interesting blend of local feature tracking, which all syntactic theories posit, and a theory of processing that would think that like a left to right processor is trying to figure out where to discharge the dependency that was created at the trigger site. But I think more could be said there. That was the set of linguistic analyses. I thought in the last few minutes, I would just open this up for more high-level discussion topics, and that might cue us into some discussion that we want to have. Does that sound okay? Do you have a question already? Go for it.
Yeah, I was just wondering, like, can you go back to the initial stage when you explained the causal model, so I can explain that question you were asking?
Or which of the analyses?
When you were giving us the analysis of how L3 and L2 has a difference of effect. Like L2 does not have an effect, whereas when you have an inference on L3, you have an effect. The initial causal model.
Oh, that was simple. Yeah, for the L3 to S1, I just showed you that they were fully aligned. And the L2 one is of interest here because I was just showing you that that L2 site could potentially have no impact on the input-output behavior of the model. And you see a lot of that here in the sense that for this problem, all those white spaces are sites where no intervention can change the predictions of the model for our tasks.
Keeping that as our focus point, I just want to ask, like, since we are aware in your way that some having inferences on some or interventions in some nodes have a direct impact and some nodes does not. And you mentioned that we'll find those localized nodes as localized nodes that have an impact on the model's results. Keeping up with his question as well. So if as the model gets deeper, what is the efficient algorithm to find if there's a specific localized node? Also, do some nodes have more effect since it's a weighted graph eventually? Do some nodes have more effect than other nodes? And how do we prioritize which node to go forward? And third question being, if L2 is not having an effect on the final result in one specific inference, we cannot actually incur the fact that it won't have a specific effect if we have to do another inference.
Absolutely right. Yeah, and this relates to I didn't answer the second half of the question about brute force search, which is about redundancy. You see, because of the transformer structure, having all of those redundant connections, you see a lot of redundant paths here. Like, for example, at a high level, you can see that the trigger part is very lexical. So it's in the lowest layers of the model, but it's spread across like the first 6 of them. And then it does persist even at points where it probably has no real impact on the output, right? Because this is hardly any effect on these points here. There are so few connections. So there's a lot of redundancy. I also think we can use this to study that kind of thing. Like you do routinely see that the lexical stuff emerges lower. And then these intermediate things that are very contextual, like the complementizer here, they tend to be in the middle. And then of course, for the thing that's actually making the prediction, it has to have a very strong causal effect, and that translates to this, this very dark spot here. For the final part of your question, this is a crucial insight. Thank you for raising this. It could be totally different for a different problem. I think that's actually part of it. Here we've got tracking of this long distance feature, but for subject-verb agreement, I think it's much more local. And so the patterns just look very different. Yeah, and that's important. That's partly what we're discussing. For my math example, it's a very simple case, but you can imagine the network does some other behavior where L2 plays the entire causal role. Those are great questions. Any other kind of technical things before we pop up a little? Yeah.
So, in the initial, when you were like starting the lecture, you were showing that with the nudge, the answer changes in maybe GPT-4o. And I mean, I've seen that whenever you nudge, alternatively, it kind of changes the answer as well. Is that an inherent intervention that the model is using the similar thing that we are having?
Oh, that's a great question. You do perform an intervention by giving the nudge. You do it at this very low level behavioral thing where you just add more tokens. something is happening internally. And I don't precisely know what it is, but that's, you know, in the context of explainable AI, this is kind of like, why does chain of thought work? Why do these prompting techniques work? We're trying to give a deeper answer than just, hey, over my data set, it does work. That's kind of what I was alluding to before about when Claude was referring to itself without saying its name. I think it's meaningful for me to ask, is it in a state of referring to itself? That is there a state where I could do a causal abstraction analysis to show that those were all it trying to say Claude? The way you and I refer in different ways to the same entities? Yeah. Yes.
So are you just looking at the hidden states of the tokens, or are you also looking at the attention weights? Because those could also possibly like tell you for, you know, a given attention head, like, you know, what is it trying to focus on, and that might also narrow down your search.
This is wonderful. Yeah, so I'm just looking at the output activation. So like if you know the transformer, all the output blocks there. But yeah, of course, you could have a hypothesis that some things will be stored inside the feed forward layers or in the attention heads. And then you can do these analyses on those structures. Yeah, we do them only on activations, not weights. But there's no reason in principle why you couldn't do them on the weights. It just has such a global effect. But all of this should be on the table.
Still another thought.
Sure, one more, and then let's do, I'll queue up a few high-level questions, but go for it, yeah.
Yeah, so do you observe a pattern in which certain abstraction or certain features are being learned in certain layers? Like other layers learning or having inference of certain other features? For example, contextual learning is happening within deeper layers or in the middle layers, whereas, I don't know, understanding of words is happening on much lower layers.
Absolutely, yeah. And that's confirming high-level insights people have had, and we see it everywhere in these analyses, that lexical things are low, which is interesting for a linguist because we say a lot of features are lexical, but some are more about the structure. And I think we see a lot of correspondences with that idea in these analyses. Yeah. Right, so just a few high-level things to wrap up here. As I said, this is my perspective. LLMs could be tools for developing linguistic theories. They're trained on an enormous amount of distributional evidence, and they evidently induce lots of abstract features and relations as part of that process. What kinds of abstractions are they learning about concepts we know about, like categories, constituents, anaphora, long-distance dependencies? And also, what new kinds of abstractions are they learning that theories might have overlooked to this point? That's where we could start to reshape linguistic theory if we were willing to be so bold. The LLM is not the theory in these scenarios. It's just another tool. You could think like, I have my eye tracking evidence, I have my traditional corpus evidence, I have introspective evidence, and now I have this new device, the language model, which gives me a new perspective on distributional information. I also think we should think about reassessing poverty of stimulus arguments, right? LLMs acquire rich knowledge of very infrequent and idiosyncratic constructions. It's just an observation. I didn't support it, but here's some papers that support that. LLMs' learning mechanisms are entirely known to us and do not include inbuilt information about these constructions. Thus, there is no logical requirement for such inbuilt mechanisms. And I emphasize that because, of course, humans might use these mechanisms. They might be very different from LLMs. But the distributional evidence alone does not establish this. There is a long history in linguistics of people just observing the distributional evidence and saying it is impossible to achieve the learning target based on that evidence, therefore something must be innate. This new world makes it very difficult for those arguments to actually go through. People should keep trying to make them, but the standard has gotten much higher, I would say. We raised this before and had a brief discussion. Neural versus symbolic. If a high-level symbolic model is a perfect abstraction of a low-level neural model, the entire neural symbolic distinction disappears. Now, I should say that perfect abstractions are unlikely to arise in nature. I only really see them in idealized examples. But that's true both of the neural networks and also of our brains, right? So I showed you a perfect correspondence between these simple networks, but in truth, it might be a partial correspondence with some differences. But that still might be very interesting for us in terms of supporting the symbolic theory while acknowledging that the implementation details introduce some fuzziness. And then finally, here's just a list of linguistic questions that I would love to address using causal abstraction analyses of LLMs. And I'm offering them here just by way of wrapping up as an example of the many sophisticated questions that I think are on the table that would inform theory and inform explainable AI. Again, I did not anticipate getting to lead a life where I got to ask questions like this with AI tools and technologies. But here we are in this incredibly exciting moment, and I'm sort of exhorting you to join me in this journey. So I'll wrap up here. Thank you very much. Thank you so much to the interpreters for helping out and for all your questions. I'm here for more of them if you like.
So thank you so much for coming. We're now going to have a coffee reception outside, but before we go, this was just an amazing, amazing talk. Another round of applause, everyone. Thank you.
Thank you.
So coffee is served outside.